Okay, this is how to pwn. Yeah, here's a table of contents. This is what we're going to be talking about. Lots of stuff. We're going to start off with shellcoding, right? Um, so essentially, shellcoding is like the most basic form of binary exploitation. So you just put like a bunch of x86 opcodes in a string, and you call it like a function. So Uh, essentially, you're just writing your own function into the like program's memory, and then you're just calling it. So this is a really easy way to get arbitrary code execution. Unfortunately, it will probably hurt like security engineers' feelings because you just absolutely dumpstered their career and they're mad. So what it looks like is we have a string in like a typical buffer overflow attack. So we would just fill the string, say we had a 64 byte string, we would just fill it with 64 opcodes, and then uh, we would just overflow the RBP with some random junk, and then the saved RIP, we would put the address of the first opcode. So then when we return after this buffer overflow, we're just going to jump to the first instruction of this string, and we're going to execute it as code. Uh, what? Okay. I thought there was a. Okay, it skipped a slide. What's going on? Here we go. This slide. Um, so this essentially allows us to run an arbitrary 64 byte program. And it's like fairly simple. There's not like any spooky magic going on here other than overflowing a return address. Uh, this is like, if you were an exploit dev during this time when you could still do this, you were probably like living life. Like you were on easy mode. There's nothing else to do. So security mitigation engineers were mad and they created ASLR. So ASLR rated with one angry face. Uh, it's not like the end of the world. It's just like somewhat annoying. So what ASLR does is it adds a constant to stack, heap, and dynamic library addresses. There's three separate constants that should be noted. Each constant is randomized per program run. So essentially, we're moving the stack by some fixed offset every time the program runs so that you can't predict where the stack is going to be. Um, so now we can't jump to our shellcode because we don't know where the shellcode is on the stack. And it's also worth noting that this doesn't randomize code addresses or global variable addresses. So this is only randomizing the stack, heap, and dynamic library addresses. So this is essentially what ASLR does. It takes these addresses over here on the left, and it adds X to them, so they become these addresses over here on the right. It's not like a super complicated mitigation technique, but it was somewhat successful. So if you notice, for our exploit to work, we would need to jump to X plus the address of the first opcode instead of just the address of the first opcode as we did before. So because we can't predict X, our exploit is essentially broken. Um, so uh, the like trivial way to, I guess not trivial, but like the easiest way to get around ASLR is to leak a stack address, and after you leak a stack address, you can calculate X. So mitigation engineers really forgot that we could print things. If we can print a stack address, we can learn X by just doing like a calculation of the offsetted address that we've leaked versus some address, some like random number that we are computing all of our other addresses by. Um, Unfortunately, stack info leaks are like pretty hard. It's hard to print a stack address. So this like way to get around ASLR doesn't really work, except in very specific cases. So stack info leaks are not a great way to get around ASLR. There are other types of info leaks that we will talk about later that are much more useful. So the easiest way to get around ASLR is to use ROP. So I've given ROP 3 stars. Instead of shellcoding, we can just reuse the code in the binary, right? So I said earlier that only the stack heap and dynamic addresses are, or dynamic libraries are randomized. So the code addresses in the binary are not randomized. So we can just jump to code addresses, and we know where they're going to be because they don't change, and we can like reuse those. Unfortunately, binaries usually don't include exploit payloads in their like source code, so we have to be like fairly creative with how we use ROP, but uh, we usually don't use it just by itself. It's not like a technique that we can use to exploit arbitrary programs. It's very much up to what code exists in the binary uh, and like other factors. So what we can do is we can use ROP to uh, like enhance our other techniques. So in a minute, we'll talk about how we can use ROP to make shellcoding work again. So I've been describing ROP for a minute. So like, what is ROP, right? Um, we we talked about this a little bit in the last talk, but for like a quick reminder, ROP is just like chaining a bunch of instruction sequences called gadgets in your buffer overflow. So gadgets are just short instruction sequences ending in a ret. So it's literally just any instructions followed by a ret instruction. And the ret is important because it allows us to chain them together in a row. So here's like a picture of this, right? This is called a ROP chain. So if we had 3 arbitrary gadgets, we could just put them in a row in our buffer overflow, and then we would call gadget 1, gadget 2, and then gadget 3, and we can chain these together to do like very small computations, but not anything super interesting. Um, so why do I care about ROP, right? Uh, it sounds like I just described something that can only uh, execute like 1 or 2 instructions uh, before like running out of usefulness. So the reason we care about this is because it gives us a lot more flexibility in our exploits. 1 or 2 instructions makes like a huge difference uh, in the world of binary exploitation. So uh, we can use ROP to essentially break ASLR for shellcoding. Um, so the question is like, is shellcoding dead with ASLR? Right? We can't we can't get a stack info leak easily. Uh, so like ASLR seems to be completely destroyed because we can't uh, like we can't figure out where things are on the stack. So shellcoding, in fact, is not dead yet because of something called .bss. So instead of putting our shellcode on the stack, which is a randomized address, we could just put it at a fixed address, right? Like it's just that easy. Just put it at a fixed address. Um, so the way that we're allowed to do this is there is like a segment in your binary called .bss, which is essentially reserved for uninitialized file scope global variables. So essentially that doesn't really it doesn't really matter what it's for, but just know that we have a big like section of writable memory that is at a like fixed address, right? So if we just write our shellcode into .bss and then call it, we will win, right? Yeah, just write the shellcode into .bss and then jump to .bss instead of jumping to like a stack shellcode.
Is BSS executable?
Uh, we'll get there in a minute. So
Okay, sorry.
in this case, we're talking about NX has not been invented yet. There is no executable or non-executable memory.
Gotcha.
So basically, mitigation engineers like forgot that fixed addresses exist, right? Kind of dumb. Uh, so here's how we would like exploit this. So we would put like a pop RDI gadget in a ROP chain, and then we would pop the address for BSS. So what that's going to do is it's going to put the address to .bss in RDI, and then we call getS, which just reads an arbitrary length of data from the user. So in this case, the user is us. So what this is going to do is it's going to read an arbitrary amount of data into .bss, and then we have .bss as the next address in our ROP chain. So then we're going to jump there. So essentially, it just reads a bunch of data from us into .bss and then jumps there. So it's like the definition of shellcoding just at a fixed address with like one ROP gadget, right? So with .bss, we run into more issues, right? Mitigation engineers are like pretty mad by this point. They didn't expect to just be like completely destroyed by this random segment in the binary that nobody ever talks about. So they go back to the drawing board and they say, okay, to get rid of shellcoding, what we're going to do is we're just going to prevent binaries from executing writable data. So if data is writable and we try to execute it as an instruction, we just immediately segfault. So now we can't use shellcode because we have to be able to write the shellcode in the first place. So this is called NX or DEP. Yeah, so like it kind of sucks, right? Now we can't use shellcode. Kind of makes us sad. The golden age of exploitation has ended. So to check if NX is enabled, there's this cool built-in tool to Pwn tools called checksec. So you just run like checksec and then like a binary name, and it tells you if NX is enabled or disabled. In most cases, NX will be enabled. These days, it's very uncommon that NX is disabled. The only time you would really ever see it is during a CTF. So kind of makes us sad that NX exists, but it's not the end of the world. So the question comes up, is shellcoding dead yet, right? And the answer is like shellcoding is mostly dead. Nobody really uses it anymore, but if you really wanted to, you could still use it. So there's a Linux library function called mprotect, which essentially allows you to change the memory flags on like some region of memory. So what you could do if you really wanted to is write your shellcode into memory, use mprotect in like a ROP chain or something like that to mark it as read only, and then use and protect again to mark it as executable. And I see in the comments, don't JITs usually have NX disabled? Yeah, that's a good point. So because JITs like write code at the same time as executing like the written code, they have NX disabled, and you can do like some pretty wild stuff. But I don't know. JIT compilers are complicated, and I don't really want to talk about them. So the point is that like we could still use shellcoding, but it's now like more work than it's worth. Like if we're gonna do this whole ROP chain to improtect and like fix the binary, it's actually less work to just exploit the binary in a different way. So this brings us to the uh, next type of exploit. I call this ROP, but smart. I don't know if there's like an actual name for it, but uh, if you really think about it, functions are just big ROP gadgets, right? It's just a big amount of code ending with a ret. Um, so pretty often we can do interesting things by just calling libc functions as if they were big ROP gadgets. Um, so for example, here's like a big ROP chain, right? Uh, and I'm gonna go through like each step of the ROP chain and like explain what's going on. So first we could like pop RDI and then put in the BSS address and then call getS, right? So this is going to read a string from the user. And let's suppose for like purpose of example that we input /flag.txt, right? Uh, so /flag.txt is written to .bss, and then the next step of our ROP chain is it's going to call open with .bss as the first argument and whatever junk is in RSI as the second argument. So what this is going to do is it's probably going to open the file /flag.txt with the file descriptor 4. So we just opened a file. And then the next few gadgets of our ROP chain are populating the arguments uh, to read, right? So pop RDI is going to put 4 into RDI, pop RSI is going to put BSS into RSI, and then pop RDX is going to put 500 into RDX. And then we're going to call read. So this is just going to read 500 bytes from the file into .bss. Oh, yeah, okay. So somebody asked, why is it probably 4? What is file descriptor 3? Uh, yeah, so in a lot of cases, I guess this is a bit of an oversight in my part. So it could be file descriptor 3, but it could also be file descriptor 4. The reason it would be file descriptor 4 is because the binary is handling its own like socket. So if the binary is like communicating over TCP, then and it's handling like its own connection, then it would open file descriptor 3 for the connection. So the file would probably go to file descriptor 4. Anyway, so we would read 500 bytes from the file into BSS, and then we call putS.bss. So this whole ROP chain just opens an arbitrary file that we specify over like text, and then prints the entire file contents back to us, right? Um, and you might be asking yourself, like, why would I ever do this? This is a lot of work. And the reason is because there's a Linux like security mitigation called seccomp that you can use to disable syscalls. So let's say uh, for the sake of argument that the like exec syscall has been disabled and we can no longer like run programs, we could use this ROP chain instead to just read the flag as if it was uh, yeah, we could just use this ROP chain to read the flag. So it's not super common, but it does come up in CTFs occasionally. Uh, I don't know if it would ever come up on one of our CTFs though. Um, it's worth noting that the previous example requires you to have these interesting functions in the binary, right? So like the source code, the original source code of the binary would have to call get s, put s, read, and open in order for us to do this exploit. So if the binary doesn't have these interesting functions in it, then we have to do something else. Yeah, and that brings us to ret to libc, which I have given all 5 stars. Ret to libc, I think, is like the ultimate like culmination of binary exploitation. Like it is the best type of exploit. So the reason that ret to libc works, I will describe what it is in a minute, but essentially when you call a libc function, there's like a weird wrapper in the binary that is used to call the function. Um, and because of this weird wrapper and because of like performance issues, it has been decided that the entirety of libc has been loaded somewhere into memory, and the like address of libc is randomized due to ASLR, but whole like the whole of libc is in memory. So including functions that we didn't call, right? Including functions that the original binary does not call in its source code. So this gets us around the ROP but smart approach where we're limited by what is called in the original source code. So if we can find where libc is in our binary, we can call literally any libc function. So calling system is a common target when you're doing this type of exploit, because uh, system literally just runs an arbitrary program that you specify the path to. Um, so generally in an exploit, you would just try to call system slash binsh, and it would replace the current running program with a shell. So the libc wrapper that I mentioned, yes. So the entirety of libc is in order. It does not randomize like individual chunks. It just puts the whole thing in memory in like one long contiguous segment, uh, all in order. So um, this libc wrapper that I mentioned, right? Uh, there's 2 components to it. One is called the PLT and one is called the GOT. That is procedure linkage table and global offset table. So um, there's the global offset table is just a big table of addresses to libc functions that the binary calls. So when the binary needs to call a libc function, it looks up the address to that function in this big table, and then it just jumps there. And the PLT is the code that's responsible for looking up these global offset table entries. So this is like the next few slides are probably the like most important part of this talk. This is essentially like how the PLT and GOT work, and like why uh, why we can take control of that to just absolutely like destroy a program. So let's say, for example, to make this wrapper like more clear, um, we'll go through an example of like what the process looks like when we call a libc function. So let's say we call printf in our source code. Um, the compiler expands this when compiling from just calling printf to instead calling the PLT entry for printf. So we would then, when we call printf, we are going to not jump to printf, we're going to jump to the PLT entry for printf. Um, and then the PLT entry is going to read the global offset table entry for printf, right? So it goes and looks up this address of where the libc version of printf lives. So yeah, this entry tells us exactly where the actual printf function is. Uh, and then we just jump to this address, right? So uh, if you notice, compiler engineers just basically installed a table of libc address leaks into our binary. And the global offset table is at a fixed address. So we know exactly where it is. Uh, so we can just leak a global offset entry, a global offset table entry, and we get a libc leak, right? Yeah, so if we leak a global offset table entry, we can easily find the libc offset and call any libc function we want. So mitigation engineers BTFO, right? They're just absolutely like destroyed. Yeah, this is the exploit devs when they found the global offset table, right? Uh, so I said earlier that we were going to come back to info leaks. I gave stack info leaks 1 star, right? Uh, libc info leaks I would probably give 5 stars. They're much more useful than stack info leaks, and they're much easier to do as well. So how do we actually do a libc info leak using the global offset table? So say we had our buffer overflow example, we could just uh, put the got address for the puts entry into RDI and then call puts, and that's just going to print to us what the it's going to print to us what the address of puts in libc is. Um, I realize now that putting got.puts here might be a little bit confusing. We could replace got.puts with got.anylibc function, and it would still work. These the fact that I have puts in both places doesn't really matter. Um,
Would this work over a TCP socket, or would this only work if you had like a standard input to the?
yeah. So depending on the way that the binary is set up, uh, I guess it depends. But you could make it work over a TCP socket by like just changing the ROP chain by a little bit. So instead of calling like put s, which is going to print to standard out, you could call like fprintf or something like that, which prints to a specific file descriptor. Uh, and if your binary is using other file descriptors, then it has to have that function in it. Um, so I mean, yes, you can do the same thing. Um, so uh, yeah, this is essentially what our ROP chain does. So we call put s of got.put s, which is going to print the libc address to put s. Um, and then we immediately call main, right? So uh, the reason we call main is it essentially restarts the program without changing the libc offset. So the ASLR is only in effect when the program is starting. So if we call main again, ASLR does not re-randomize all the addresses. So we've essentially just leaked a libc address and then restarted the binary. So now we can compute the base address of libc, and we can just do another ROP chain in like the same vulnerable function, right? So after we've done this, we now know what the libc offset is, and then we could just do something like this. So we could do pop RDI, libc binsh plus offset, and then libc system plus offset, right? So Uh, it's kind of interesting that libc almost always contains the string /bin/sh somewhere, which is really useful for us because that is the program that we want to call. So uh, we just pop this string into RDI, and then we call system, and now we have a shell, right? Pretty cool exploit. Um, yeah, this is what people that know how to do ret to libc look like. This could be you uh, if you if you try ret to libc. I assume we will probably have one at future CTFs. Um, and then this brings me to the last point that I want to make, which is global offset table overwrites. Um, so the global offset table is writable. So if were to overwrite a global offset table entry, all future function calls to that entry are going to go to the address we overwrote instead. So if we can find a way to overwrite global offset table entries, we don't even need buffer overflows anymore. Like we can just call functions and it's going to take us to the wrong place. Um, so the like rest of this exploit is a bit out of scope for this talk because we're only like concerned with buffer overflow exploits currently. But like a lot of like printf exploits and heap exploits use this method, so it's good to be aware of. And there's also times where you would run into issues with a typical buffer overflow that would require you to do this as well. Um, so that is the end of the like content of the talk, um, and now is the time for questions. I guess I see in the chat somebody said, what makes it infeasible to randomize the libc contents? So people actually do this. So if we go way back to this slide, there's this thing called PIE, right? That's position independent executable. Um, so that's what PIE is. So instead of randomizing the libc addresses just as one big chunk, uh, actually, I don't know if PIE even affects libc. So PIE is essentially to randomize code addresses, right? Uh, the position independent part means that like uh, if we take uh, a bunch of like code in our binary, that we can put it anywhere and it's still going to run the same. So you split the binary up into a bunch of little pieces and then you randomize all the little pieces, and it does a bunch of magic to figure that out. Um, I don't actually know if libc works with pi, like, or rather, if pi is used on libc. Does anyone know? Okay, libc is pi. Okay.
Would there still need to be a global a dot
Yeah,
that
yeah.
could
So
still then be exploited? I'm just thinking like it seems like it it's weird to think that there's not a workaround for like defensive security engineers. It seems
yeah,
like there
so
maybe could be.
so with PIE, the global offset table actually becomes way more interesting because like all of these uh, like random addresses have to go through the global offset table. So um, if your binary is trying to like look up where to find like variables or where to find code, it has to go through the global offset table because like the code could be randomized. Yeah, yeah. Tristan
Thanks.
says, I think libc has to be PIE because if it wasn't, it couldn't be loaded at a random address. Um, yeah, that's true. Cool. Does anyone else have questions? I guess we can stop